This video is a criticism of the NASA video, Moon Machines, the Lunar Rover. It shows problems it contains. Initially, plenty of versions of the lunar module were built. They were more looking like agricultural machines than space rovers. At start, nobody was knowing what the lunar surface was like. It was not known if it was possible to make a vehicle with wheels ride on it. Finally, a space vehicle could get close enough to the lunar surface to have a quite good look of it. It crashed at the end, but it could send images of the lunar surface till it crashed. However, at the rate that it was sending images, and the great speed that it crashed on the moon, it couldn't get very close images of the lunar ground. NASA would have later sent surveyors softly land on the moon. However, a surveyor cannot land on the moon like it would on Earth. Indeed, there is no air on the moon, and it can't use a parachute to land softly. The space engine carrying it was initially orbiting the moon at a very high speed, around 6,000 kilometers per hour, and surveyor descended along a very long parabola which was mainly horizontal. It couldn't descend vertically all along its descent, and it would have needed a quite powerful engine to decrease the important orbital speed. The exploration of the lunar ground made by the surveyors would have shown that the lunar ground was apt to support the wheels of vehicles. If of course it had otherwise, how would have they made the Lunar Rover ride on the moon? They first built a big-sized laboratory exploration pressurized vehicle which would have been able to allow astronauts to survive during 2 weeks on the moon, thus allowing an extensive study of the lunar ground. There even a man who tested it on Earth. But only a giant rocket would have been able to carry this monster, and sending a huge rocket to the moon and making land on it was the initial idea of von Braun. However, it soon became obvious that sending a big rocket to the moon was not technically feasible. Only a couple of two smaller spaceships, according to the idea of John Houbolt, could make it. Von Braun finally realized that Houbolt's idea was the only possible alternative to succeed a lunar landing, and it was excluding using the big laboratory vehicle. But if it was not possible to send heavy vehicles to the moon, it still was possible to send lighter ones that smaller spaceships could carry. Indeed, in the lunar module there was a compartment available, but was it large enough to contain a lunar rover? A full deployed lunar rover? Certainly not. But if this lunar rover could be compactly folded enough. A small model of lunar rover was first made. It was conceived in such a way that it could easily be folded, and that it could hold in a relatively small box once that it was folded. The small lunar rover model is driven into von Braun's office, who is very surprised and delighted. A short film finishes convincing him, and he adopts the idea. Now that the idea had been agreed, a real-size lunar rover had to be built. However, the weight had a critical importance. More weight was meaning more fuel burnt when landing. Neil Armstrong only had a half-minute fuel remaining when he landed. Although when we see the lunar ground on the video of the landing it appears obvious that he could have landed sooner, for we see no major obstacle which would have prevented the landing. Ordinary rubber tires could not be used. A new type of tire had to be invented, a tire which could ride in the void of the moon and could not go flat. So a new wheel casing was conceived, made with reinforced wire mesh instead of rubber. The wire mesh tire is tested on a test bench. However, in this test, the wheel is maintained over the conveyor. It is not weighing on it like a wheel mounted on an axle tree would do. Each wheel was driven by its own electric motor. There also was the problem of temperature. If the temperature was becoming too cold or too hot, all the batteries would cease to work, and the rover would stop. A conventional cooling system was too heavy, so a lighter one was invented, and, according to the engineers, it was quite efficient, so they say. The Lunar Rover also had to prove it could correctly deploy. But in a demonstration, the deployment stopped at the middle of the maneuver and got stuck. Fix it or leave it was the warning. The accident of Apollo 13 showed that going to the moon was quite dangerous, and was far from being a safe trip. So the justification for further missions was to make a scientific study of the moon, and not just to go for the show. And the Lunar Rover would help in this scientific study by allowing the astronauts to make longer trips. Scott tries the new Lunar Rover, but this Lunar Rover obviously has ordinary rubber tires, and not the wire mesh ones. And the test was relatively short, while the Lunar Rover was supposed to be able to ride for 4 hours long either. The Lunar Rover is also tested in reduced gravity, by using suspension wires to lighten the gravity. However, the ground on which the rover is riding only has small rocks, far from the quite big rocks we can see on the photos of Apollo 17. A TV camera is added to the rover equipment, not to the satisfaction of the engineers who consider that it isn't overweight for the rover, while they are trying to keep the rover's weight as light as possible. This camera will be able to film the activities of the astronauts on the moon. The orientation of this camera can be controlled from the Earth in 2 directions, horizontal and vertical. It can also zoom in and out. However, there is a difficulty in the control, which is that, between an action that the operator makes on Earth on the hand controller which controls the camera and the result he sees on the screen, there is a delay of 2.5 seconds, 1.25 seconds to send a command to the moon, and 1.25 seconds for the corresponding image to come back to the Earth. It makes more difficult the fact of following quick moves like the liftoff of the lunar module. Finally, the first operational Lunar Rover can be delivered in time for the Apollo 15 mission, which will be the first mission to use a Lunar Rover. Apollo 15 lifts off with the Lunar Rover inside. At least this is what we are supposed to believe. The rover is successfully deployed on the moon. . But there is however a problem. When the astronauts checked the rover, they realized that the front wheels cannot be steered. Fortunately, the rear wheels still can be steered, otherwise the Lunar Rover could not have been used apart from constantly going straight. Yet you know that it is easier to control a car when it goes forward than when it goes backward, and not only because of the difficulty of looking backward. Turns are easier to take when going forward than when going backward, and maintaining the vehicle on a straight line is also easier. That's why on all the vehicles, it's the front wheels which are steered and not the rear ones. That does not mean that the Lunar Rover could not turn if only the rear wheels could be steered, but it means that it was not as easily maneuverable as if the front wheels could have been steered. So, in the logic of Apollo, if there was a choice between the front wheels or the rear wheels which could not be steered, it definitively had to be the front wheels. Like Murphy's Law absolutely had to be respected. And seriously, does it make sense that the steering of the front wheels would not have been tested before sending the Lunar Rover to the moon? The rover is now riding on the so-called moon. But what is exactly the TV camera filming on this sequence? This sequence has been used by the Apollo believers to sustain that the dust which spurts behind the wheels could only have fallen on the moon. But if you attentively look at this sequence, you can see that the dust does not directly spurt from the wheels, but a little after. That means that it is something else which makes it spurt, something which is not in the field of view of the camera. And what do we see on this sequence? What are these white flakes falling over the rover? Is it snowing on the moon? The liftoff of the lunar module could not be accurately filmed in Apollo 15, because the TV camera got stuck and refused to move up. There also was a problem in the filming of the liftoff of the lunar module on Apollo 16, for the operator did not manage to adequately keep the lunar module in the field of view of the camera. He had difficulty to follow the move of the lunar module. In Apollo 17, however, he started to have some experience, and he managed to follow the lift of the lunar module for some time. So we could see that the engine of the ascent module had no plume, and also the consistent swaying move of the lunar module with an increasing amplitude some time after the liftoff. And finally we also see the liftoff of the lunar module filmed from inside the lunar module, and what we see is an irregular ascent which defies the laws of physics. Now here are some facts which make strongly doubt that the rover ever rode on the moon. They put a dust cover over the batteries while the rover is moving in order to prevent the lunar dust from coming onto the surface of the batteries. They only remove the cover when the rover is parked near the LM, to allow the recharge of the batteries. But it makes no sense on the moon. Unlike on the Earth, the dust cannot billow, and there is thence no reason that dust would come over the batteries. On the other side, leaving the batteries exposed to the sun would allow the batteries to charge a little while the rover is moving, and would thus allow to increase the range of the rover. This is the scheme of the console allowing the control of the lunar rover. On the left side of the console, there is an angle indicator which allows to inform the astronaut about the rover's angles around the horizontal axis. This indicator is a box which contains two angle measuring systems which are placed in perpendicular to each other. These angle measuring systems use the principle of the pendulum to work. They use the lunar gravity in order to know the exact vertical, They are of course more sophisticated than what I show here, which is only intended to explain the principle of the measure. These systems measure the rotation angle around the axis which is perpendicular to their plane, and that is why they are placed in perpendicular to each other. The roll angle is the angle of rotation around the lengthways axis of the rover, and the pitch angle is the angle of rotation around the horizontal axis which is perpendicular to this axis. Normally the indicator is oriented so that the astronaut can read the roll angle in front of him. If he looks on the left side he could read a pitch angle, but it is not very convenient for him to read it that way, not to say impossible. That's why the astronaut has the possibility of manually turning this indicator of a quarter of turn counterclockwise, so that he can read a pitch angle instead. But this is ridiculous. If he turns the indicator of a quarter of a turn, the two measuring systems are also going to be turned of a quarter of a turn, which means that the one which is supposed to measure the roll angle will in fact measure the pitch angle, and vice versa. Although the angle reading that the astronaut has in front of him is now labeled pitch, it is still a roll angle that the astronaut will read. Turning the angle indicator does not help. If the astronaut really wants to know the pitch angle, the only solution would be for him to try to read it on the left side of the indicator as it is in normal position, which is practically impossible for him. The documentation says that the pitch and roll angles are sent to the navigation system to update the navigation, but if the astronaut turns the indicator, not only it will not allow him to read a pitch angle, but furthermore the navigation will misinterpret the angles and will use the pitch angle instead of the roll angle, and vice versa, since the rotation of the indicator is purely manual and the navigation system is not informed of this rotation, and thence does not know the angles are swapped. As the moon has no magnetic pole, a magnetic compass would not work on the moon. When Charlie Duke was interviewed by James May and asked how they were managing to orient themselves with the rover and find their way back to the LM without a magnetic compass, Charlie Duke answered that they just had to follow the rover's tracks back to the LM. Charlie Duke was not even knowing that the rover was equipped with maps, circled in red on this close-up of a photo of Apollo 15, and a solar compass, circled in green on the same close-up. The problem with this sun shadow device, which has been circled on the scheme of the display console, is that it was only working under a restricted angle, and could not cover all the possible angles. In fact, it could only work when the rover was oriented so to have the sun in its back, while a compass can work in any orientation. So why not provide the astronauts with a real sun shadow compass, which can work in any orientation of the rover, like the one which is shown on this photo. The odometer is a device which is fixed on a wheel and allows to measure its rotation, and obtain from this measure the car's speed and the distance it covers. In the mission report of Apollo 15, it is stated that the distance recorded by the odometer was quite close to the prediction, which suggests that it would have quite well worked. But the astronauts do not seem to agree with this statement, for here is what they say while driving at Elbow Crater. Scott, hang on. Get a feel for this thing. 9 kilometers an hour, Joe. Oh, and it seemed like we were going much faster. Jones, because of the roughness of the terrain? Owen, I guess so. But also remember, we've never checked the rover navigation system, so we don't know it's right. It may say 1.3, but we may be at 1.9 or 0.7 because we'd never done this before and there was a question of wheel slippage. You know, if your wheels slip a lot, your odometer is going to turn a lot, and you're going to think you're a lot further than you are. So we don't really have confidence in the nav system at this stage of the game. In the documentation they say, the odometer logic cannot distinguish between forward and reverse wheel rotation. Therefore, reverse operation of the LRV adds to the odometer reading. That means that the rover cannot make the difference between going forward and going backward. Yet it is important for the navigation that it could make the difference. An example to show the importance for the rover of making the difference between going forward and going backward. Let's start from this position of the rover relatively to the LM. You can see that, if the rover moves straight the same distance forward or backward, the new orientation of the rover relatively to the LM will not be the same. This is why the navigation needs to know, not only the distance the rover has ridden, but also in which direction. The astronauts had a reset button to initialize the navigation system at the start of the mission. This button was setting all parameters to 0. The problem is that they could change this switch at any moment of the mission. There was no protection against using it in the middle of the mission, yet, if they use this button in the middle of the mission, the navigation will lose its current data, and will become unable to make a correct update from that moment, for the navigation updates new position from a previous one. The navigation system also had to be reset in case of temporary power loss. In the documentation they say that the rover had to ride 50 meters after the start of the reinitialization before the data of the navigation station were valid again. So imagine that the rover has a problem which makes that it cannot move anymore at that precise moment. If the astronauts have to come back on foot to the LM, they have to know in which direction the LM is, otherwise they might be incapable to go back to it. But the rover had to ride 50 meters before the navigation station gives a valid indication, and it can't. So what are the astronauts going to do? Carry the rover on 50 meters till the navigation station gives valid data? But the wheels of the rover probably need to have contact with the ground, so the astronauts are going to push it on 50 meters instead. Let's be serious. If the navigation system has lost a valid reference, there is no way that it can acquire it again all by itself. After having ridden 50 meters, the navigation will have updated from an invalid reference, and will still have an invalid reference. The only way to reinitialize the navigation system would be to give it a valid reference. The only solution would be to emit a signal on an antenna, and orient this antenna to get the best signal in return. From the LM, the distance of the LM could be acquired by measuring the delay between the emitted signal and the received signal. But, and that's the whole problem, the navigation system is incapable of orienting the antennas itself. Both are oriented manually by the astronauts. They have provided for a commanded rotation of the camera, but they have provided nothing for the automatic orientation of the antennas. Yet, allowing the antennas to be remotely oriented would have allowed not only to automatically orient them so to always have the best reception, but also would have allowed to make a reinitialization of the navigation system, and this is essential for the safety of the astronauts, for if they don't know where the LM is, and are incapable to go back to it, it might mean death for them. But sending images to the Earth is more important than the safety of the astronauts, isn't it? So, to conclude, once that the navigation station has lost its reference, there is no way that it could acquire it again because nothing has been provided for it. This is the way that the documentation shows that an astronaut was strapped with his safety belt. If a cop was seeing you strapped like this in your car, you might be sure that he would give you a ticket for being unsafely strapped. This seat belt certainly does not guarantee the safety of the astronaut. When the rover was deployed, it was almost a naked frame, for it would not have been possible to fold it with all the equipment on it. That means that the equipment had to be mounted on it after the rover had been deployed. But the reality is that it would have been impossible for the astronauts to mount the rover's equipment with their pressurized gloves. Besides, we don't see the astronauts make this mounting work. When we see them busy near the rover, the equipment is already mounted, so they probably had assistants who mounted it for them on the moon. The astronaut had to climb on the LM to reach the deployment handle, so the engineers were not able to devise deployment handle placed lower, which was not forcing the astronaut to play the acrobat to reach it. This figure shows how the TV camera was installed. Two support posts for the LCRU, respectively circled in red and green, go into two inboard receptacles, also circled in red and green. But what's strange is that the distance between the two support posts is consistently greater than the distance between the two inboard receptacles that they must yet go into. Are the distances elastic on the rover? On this photo of Apollo 17, referenced AS 17-134-20453, there is something strange if we make a close-up of the battery. Seriously, how is it that the battery can appear so seriously damaged? Some Apollo believers have tried to explain that the battery is not damaged, but that there is something which shades it. The problem with their explanation is that there is nothing above the battery which is shaped like this shadow, and in the middle of the black part we see a bit of the battery which is obviously lower than the rest of the battery. If we compare the support of the TV camera on the photos AS 17-134-20453 and AS 17-134-20477, why do the screws of the support appear much whiter on the second photo than on the first one? You might say that it is because this side is more lit on the second photo than on the first one, but you can see that this is not the case. The majority of this side is duller on the second photo than on the first one. The explanation of this side being more sunlit to explain the white screws could eventually fit for the upper edge, but not for the lower edge. On this photo of Apollo 15, referenced AS 1592-12434, why does the top of the passenger seat appear abnormal? On this photo AS 1585-11411, on the side of the wheel's shadow which is closer to the photographer, we can see the shadows of the rivets which have been circled in green. But on the opposite side of the wheel's shadow, on the part which has been circled in red, we can't see the shadows of the rivets. Have the rivets gone on this part of the wheel? On this photo of Apollo 17, AS 17-146-22296, there are metallic curved plates which support the wire mesh. Two of them are indicated with arrows. These metallic plates are regularly spaced all along the tire. But why are they missing at the place which is indicated with an interrogation mark? This animation has been made with 4 photos AS 17-133-0295 to AS 17-133-0298. In order to better follow the landscape, 2 perfectly recognizable holes have been circled with 2 different colors on the 4 photos, so we can see how they move in the animation. The way that the TV camera appears on the photos, the rover is normally approximately moving toward the direction indicated by the green arrow. But the way that we see the holes move on the photos, it would be in fact moving in the direction indicated by the red arrow. NASA hasn't told us that the rover was able to ride sideways. The best sequence with the rover is probably this one. In the Apollo 17 library video, the engineers say in a comment that, in order for the video which is filmed by the camera of the rover to be correctly transmitted toward the Earth where it was watched, the high-gain antenna, the one shaped like an inverted umbrella, had to be correctly oriented toward the Earth, and they show this video to go with this comment. You can see that on this video the antenna of which we can see the shadow plays a gig, and certainly does not remain correctly oriented toward the Earth. And in spite of this, the quality of the video does not suffer from it, and remains the same all along the sequence, which is contradictory with what the engineers said. But all these problems don't prevent the Apollo believers from having an absolute fascination for the lunatic rover.